Hey guys, welcome back. In this video, we're going to take a look at 11.6, the wave model of the atom. This, it's going to get a bit strange. And so let's just sort of think about what we've done with our atomic models. We started way back with James Dalton, and then we moved to J.J. Thomson and the cookie dough model, and then we moved forward in time to Ernest Rutherford and the gold foil or the nuclear model. Then we move forward in time to Niels Bohr and the planetary model, and now we're up to something called the wave model of the atom. And here's kind of how it started. In the 1920s, these two guys are as much responsible for this model as anybody, though there were a fair number of other people involved. The guy on the left is named de Broglie, or de Broglie perhaps in French. In 1924, he wrote a thesis that claimed that electrons and any other subatomic particle like protons and neutrons could be treated as waves. And this was a fairly new idea. Nobody had thought of doing that. People thought about these things sort of as, like little baseballs or something that are just interacting with each other. And de Broglie said, no, they're waves. And it was remarkable. 5 years later, he got a Nobel Prize for his PhD thesis, that might be the only time in the history of humanity that's ever happened. Usually people have to be pretty established scientists before they're even considered for Nobel Prizes. The other thing that happens is some people wait decades to get a Nobel Prize. And so everything really fell into place nicely for de Broglie. On the other side, you've got Schrodinger. Schrodinger was born in Austria, and he was trying to work on incorporating a few things, but very much de Broglie's idea of treating particles as waves. And so Schrodinger sort of famously went to Switzerland, I think, to go skiing with his mistress. And while he was on vacation there for a week or a week and a half, it just occurred to him, this formula, a mathematical formula, occurred to Schrodinger. That's not quite fair. He had been working really, really hard on this, right? But he kind of let his brain relax a little bit, and bam, it appeared to him. Let me show you this formula that Schrodinger came up with. This is it. You might recognize the equal sign, but that's probably about all you'll recognize here. These things here with the parentheses t, it's a function of time. These are called wave functions. You might recognize the I. That's used in imaginary numbers if you've studied those. But that's probably all that looks familiar. But this is some math. And basically what it does is you feed a function into it, and this operates, sort of chews on the function, it spits something out. Well, what does it spit out? These shapes. All this Schrodinger equation does, and you don't have to memorize it, you don't have to use it, I'm just showing it to you so you appreciate that there's that the boundaries of human knowledge go well beyond what we do in this class. But you feed wave functions that sort of describe particles into this, and it chews on them and it spits out these shapes. And we're going to grapple with these shapes in the next couple of sections. Right, so electrons are waves. Now here's where it gets a little interesting. Niels Bohr talked about electrons as being on these rings, these energy levels. So we'd have the nucleus right here in the center, and then in the planetary model, the electrons just orbited the nucleus on these rings. Okay, so now we're not treating electrons as particles anymore. They're not baseballs anymore. Now they're waves. And so this wave is waving. Rather than going around the ring like a bead on a wire, it's a wave that's just vibrating back and forth, right? Now in a wave, you have these points right here where they intersect. Those are going to be called nodes. And those nodes are going to come up again later on. So a node is a point where there isn't any vibration. There's an intersection there. And then between the nodes, you have these points of maximum vibration. Those are called antinodes, and we'll see those later on too. Now, earlier we said it takes a very specific amount of energy to go from one ring to another, like this. If this electron is going to go from the third ring and drop down to the second ring, it has to emit a very specific color of light. And that specific color of light is where all of these lines are coming from, right? Well, all right, we're going to think about this in a slightly different way now. We're going to say that only certain wavelengths fit perfectly around this ring. Wavelength is another way to say color. So only certain colors of light will fit perfectly around that ring. Yeah? You say, well, why can't I just stick any old wavelength? Well, here's just a random wavelength, up and down, but it doesn't match up. You see, when you get back to your original starting point, it doesn't fit, right? This is kind of an interesting idea because it's a trick that nature goes back to over and over and over again. These things are called standing waves, and they pop up everywhere from organ pipes and music to drum heads to water flowing down the river. I mean, standing waves are literally all around us. And the idea here is that this is not allowed, right? Because these don't match up. This is allowed because if you start right here and you go all the way around the ring and you come back, boom, they match up, right? And then here's another picture of that, indicating wavelength here, right? So this is the way we're thinking about electrons now. Electrons are waves. That's hard because intuitively we all understand baseballs, but waves are a little trickier for us intuitively. All right, so electrons are waves. So what? Well, what that led to is something called an orbital. It's an unfortunate word because it has nothing to do with an orbit. Orbitals are about where you are likely to find electrons, which is very, very different from an orbit. In an orbit, you can point to exactly where the object is, right? So if you think about the Earth going around the sun, we know exactly where the Earth is right now, and we can tell you where it's going to be a month from now and where it was a month earlier. That's not the case with orbitals. In an orbit, maybe you can take a picture, so to speak, and find where an electron is right now. But that tells you nothing about where the electron was 10 seconds ago. It tells you nothing about where the electron's going to be in 10 seconds, right? Orbitals are a region of space where you are likely to find an electron. Orbitals are a region of space where you're likely to find an electron. What this means, what's this picture? What's happened here is we've got the nucleus at the center, and then we took about 1,000 snapshots, so to speak. Imagine that the electron is buzzing around, sort of like a fly buzzing around a light on a hot summer night. And we just open the shutter 1,000 times, and every time we take a picture, the electron's in a different spot. But what we find is that the electron is more likely to be in these very dense spots, and it's less likely to be out here, right? And what's interesting is it's never out here, yeah? Okay, so you take 1,000,000 snapshots, and then you say, well, look, this is hard to draw. I want something I can draw. And so that's where this comes in, right? This is sort of the definition of an orbital. You've got a 90% chance. An orbital is a region of space where there's a 90% chance you'll find the electron inside. So it's almost like we have two lemons, one here and one here, or two balloons, one on the right and one on the left. And then what we do is we just shade these in. We get rid of all the dots that were on the outside, and we say, this bottom shape is an orbital. It's easier to draw, it's easier to visualize, but it has two problems with it. The first is that people forget that the electron could be outside of here. It's just that there's a 90% chance it's going to be inside there, right? If you take 100 pictures and 90 of those pictures, the electron's going to be inside this shaded area. But in 10 of those pictures, it won't. It's going to be out here somewhere. The other thing that people forget is that nature's not this clean. We look at these nice computer-generated shapes that you're going to see for the rest of the chapter, and we say, well, okay, that's the shape of an electron. That's the shape of an orbital. This is what nature really is. This is just an easy way for us to represent it or draw it, right? And it's easy to lose track of that. Here's another way to think of this. This video is being shot in the spring of 2020, and so we're in the midst of a pandemic. What we all would like to have is, say, we're in the middle of it, we'd like to have, bam, a sharp edge. We say, today we're in the pandemic, tomorrow it's done, we can go back to life as normal. That's not how the real world is, right? A more accurate analogy is we're right in the thick of this pandemic, and as the weeks and months go by, it's slowly going to peter out. So that 20 years from now, when your kids say, hey, mom, dad, when did the pandemic end? You're not going to be able to give them a date, right? There's no sharp line. You're going to say, it sort of slowed down over the course of 2020, the spring and fall of 2020, God willing. This is real. This is made up to represent that. Yeah. All right. Well, there are different kinds of orbitals. I'm showing you two right here, but there are more besides, and you'll learn about a few of them. This has circular symmetry, so to speak, and it's called an s orbital. The s actually stands for sharp. It doesn't matter why. It's just an s orbital. This is a slightly different shape. This is a p orbital, and you don't have to memorize those quite yet. You should keep these in mind, but you'll also be introduced to d orbitals and f orbitals. There are more, but we're going to stop with those. So these are a couple of the most common shapes that we'll be working with. Again, what it means is you're very likely to find the electron close to the nucleus. In a p orbital, you're very likely to find the electron in some kind of a plane, right? Sort of a horizontal plane. Orbitals represent probability. What happens when you start treating electrons like waves is you absolutely cannot say where an electron is going to be. In fact, it's almost more than that. It's not just that we can't say it, it's that the electron does not have a precise location. That's a little weird. We're used to things being in places. You may not know where they are, but they're somewhere, right? You're looking for your car keys. You say, well, I don't know where they are, but I know they're someplace. If I just look long enough, I'll find them. That's very different than saying, no, your car keys don't have a location. And if you're saying, Cato, what's going on? That doesn't make any sense. That means you understand the claim, right? Electrons truly do not have a precise location until you measure it. And so what we would do, you'd say, well, this kind of looks like the p orbital, right? There was that sharp plane, kind of two lobes, one on the left, one on the right. All we've done is turn it upside down. So now we have one lobe on top and one lobe on bottom. We're very likely to find the electron above the axis. We're very likely to find the electron below the axis. But what's interesting is you will never find the electron on the axis. It cannot be there. Where did it go? Blammo. Right there. That's the same thing, right? The electron's never right in the middle there. Right there. There's a node, right? There's a node. That's what we're looking at. This is a node. And you'll notice that between the nodes, right? Between the nodes are the maximum vibrations. Maximum vibrations. All right. Node, maximum probability of finding the electron, maximum probability of finding the electron. Bueno. I'm going to clobber you with one final thing here, and then we'll stop. Orbital shapes are around us, even though we don't think of it because we're not used to thinking that way. Here's one, right? We've got a big jump, and then nothing over here and nothing over here. Let's take a look at these. Well, here you've got it, right? You've got, oh, jeepers, you can't see that, can you? All right, let's look at this one then. We'll just look at this. Here you've got this vibration. This is a drum head, right? The drum head is attached to the rim on the outside, and it's going up and down, up and down. That's exactly what's happening right here. Up and down, up and down. Now in this one, we've got a little up and down and a big up and down, but we've got a node right there in the middle, haven't we? All right, a big up and down and a big up and down with a node right in between. That's the way a drumhead vibrates. We can't see it because it's happening much, much too fast, and it's certainly not vibrating this much, but that's the way it's happening, right? You can also think of this if you watch somebody drop a rock into water in slow motion, you see exactly this kind of motion. Nature goes back to the same bag of tricks, whether it's electrons around an atom or dropping rocks in a pond or vibrating columns in an organ. All right, up and down, node, up and down, node, up and down. Well, here it is. Up and down, node, up and down, node, up and down, right? Maybe these pictures are just a lot of gobbledygook, but what do you take away from this section?